Welcome to the Pentair Learning Center. This webinar will be on the pump curves. We're going to review basic pump curves. More importantly, we're going to look at how the pump curve is created, because understanding how the pump curve is created will then lead right into how to size a pump. So if you understand one, you'll understand the other. I'm Dan Featherstone with the Pentair Learning Center, and let's get going. Now, if you're watching this on the Pentair Learning Center, you obviously know how to get there and you've already signed up. But let you always know there's many different opportunities for learning with our company. If you go to any of our websites, under the Resource tab, on the left-hand column, go down to Learning Opportunities. You can find all of these here. So the Pentair Learning Center, as you know, is an interactive e-learning modules. Live and recorded webinars are presented there. You can also follow us on Facebook. We do have updates there and telling us where we've been, where we're going and such, and other opportunities for you to catch us. Pentair Pro Dealer Program, I always like to mention that, especially for, if you notice, one of them is the labor and extended warranty programs that are available. If you're not taking advantage of this, you're really missing out. And like any company, of course, the rewards, you can get reward dollars and use them as such. More details are available at www.pentairprodealer.com. We also have an access portal for our dealers and distributors. Gives you 24-hour access, 7 days a week, to pricing, availability, order status, etc. There's no cost. Give Miss Amy a call at 866-880-3771. She'll be happy to help you. And of course, last but not least, we always have live school events. We have our official ones that we host. But if you want to see me out there in the field, contact your salesman or your dealer and distributors. They can get a hold of us and make arrangements if you'd like to see us out there to do some one-on-one. When you come to the factory schools, we have the water systems and the ag industrial. Both of these, I want you to know, it's not just lecturing. We don't like to have you sit for more than 90 minutes. We try to get you up and moving and doing labs and seeing demonstrations and such. So again, if you want to register, go to any of our websites. They're out there. You can sign up to great value. We hope to see you there. Okay, now to get started, like I said, today we're talking about the basic curve. So we want to talk about first how a curve is created. And if you understand how the curve is created, you kind of then understand how sizing will work. So we're going to talk about the basic information needed to size a pump, and then we're also going to tell you what the curve is trying to explain to you or demonstrate to you when you have your numbers. If you look at any basic curve, you're going to have basically flow that will be typically on the lower axis or the horizontal axis, and you're going to have total dynamic head, which is going to be on the vertical axis. What you'll see is that it might be in gallons per minute for flow. It might be in meters, meters cubed, liters cubed, however it's going to be expressed. But typically, again, on the horizontal will be gallons, and on the vertical you'll have feet of head, maybe meters, however you wish to show that. But that's how basically all curves are set. Now, we know how the curve is set up, but how do we get the information to populate the curve? And we're going to set up a pump, and this is through a centrifugal, but submersibles are done basically similarly, just looking at the discharge per se. Now, to make this simple, we'll talk about a centrifugal, and on that centrifugal, 2 times the pipe diameter, we're going to put a combination gauge that will show suction and pressure. Okay. Now, 5 times the diameter, away from that gauge, we're going to set up a valve to control the flow to mimic different types of depth to water and such by reducing and restricting the flow. So we'll have a valve. Now, coming off of the discharge, 2 times the diameter of the pipe size, we'll have a pressure gauge. Now, what I mean by 2 times the diameter is, for example, if the discharge pipe is, say, 3-inch pipe, so 2 times 3-inch diameter would be 6 inches. About 6 inches above is where we put that pressure gauge. Okay. Now, 5 times the diameter from there, we're going to have the flow meter, which should tell us how many gallons per minute we're producing. So you kind of get a picture here of what we're doing. We're setting up our suction. We're then going to measure the pressure, and we're going to measure the flow. And of course, in order to control the flow, we're going to have a valve up there higher on the discharge to do so. All right, now knowing that's how we set this up, our engineers then would have the flow so it shows 0 foot of lift. Basically, the water is free flowing into it. So they set up their suction side, they then get the discharge flowing, and then they'll close off that valve all the way to get the maximum pressure the pump can build, and they'll record it. Then they'll open up the discharge valve to get, say, 5 gallons per minute of flow, and adjust the valve on the suction to make sure it's at 0 feet of lift again, and they'll get the pressure reading for that. And then they'll go to 10 gallons per minute, 15 and 20, 25, until the pump runs out of available water production due to the size of the impeller. So they'll record this. And like I say, they'll bring it to this portion here where you'll see that at 0 gallons per minute, the pump is producing about 148 feet ahead. Let's call it that. And as you go, you'll see that they'll actually record only the 5, 10, 15, 20, 25, and the run out. That is the maximum gallons per minute the pump can produce at the end of that curve. And then they extrapolate or draw in a line to show you all the data points and connect them. And one question I always get is people ask me, well, why at 29.5 gallons per minute? That's run out. You're no longer producing any more gallons per minute than that. Why does it not go to 0 feet of head? And the simple answer is because at full run out, it's still producing pressure. So we have to show that. We have to reflect that upon the curve. So now I also want you to understand the pump right now we're talking about is a single speed cross the line contactor, meaning being run by a pressure switch, for example. So the point's closed and that pump's going to run at one set speed. Knowing that, I want you to understand the pump can only do what the curve will allow it to do. Okay? Now, meaning that if you look at 15 gallons per minute at 150 feet of head, is that pump going to achieve that? And the answer, a lot of people will say, well, that's easy, Dan. That's above the curve. It's to the right of the curve. It's beyond what the curve can do. In fact, I already told you the pump only does about 148 feet of head maximum. So at 15 gallons per minute, it will never hit 150 feet of head. What it will hit is at 15 gallons per minute, it will hit about 120 feet of head. Okay, 120 feet of head. So the pump can only do what the curve will allow it to do. Knowing this, here's my next question. At 10 gallons per minute, can we hit 100 feet ahead? And I'm pausing for you to kind of ponder this because, yes, it's a trick question. No, it can't. And everyone say, well, wait, Dan. It's to the left of the curve or below the curve. Anything below the curve the pump can do. No, it cannot. Remember, this is a single speed unit. It can only do what the curve will allow it to do. So if I restrict the flow to 10 gallons per minute, that means my discharge would be 132 feet of head. If you will, extend that 10 gallons per minute line straight up and you'll see it crosses at 132 where it meets the curve. Now, let's say we restrict flow or pressure. If we restrict pressure this time, look at 100 feet of head, draw that line continuing to the right, and where it crosses the line, the red curve is actually at about 20.5 gallons per minute. So at 100 feet ahead, it's either going to try to do 20.5 gallons per minute, or at 10 gallons per minute, it's going to try to do 132 feet of head. But it can't do 100 feet ahead at 10 gallons per minute. Okay? Because this is a single speed unit now. Now, a lot of times people will talk about, well, how can I adjust it? How do I make that whole curve different? And prior to variable frequency drives, we would trim the impeller, is what it would be called. And we would literally cut the radius of the impeller down, because by reducing the radius of the impeller, we reduce the velocity of the water, which directly imparts less total dynamic head. So by cutting the impeller trim down, we now have a totally new curve. Also remember, trimming an impeller means we have physically cut away material. So now we change the whole entire curve as shown, meaning that 10 gallons per minute at 100 feet of head is obtainable. We can now do it. But in order to do that and cutting the impeller down, we will never do 100 feet ahead at 20.5 gallons per minute again. The old curve would have let us do it, but because we've physically taken away material from the impeller, we no longer can do that. A lot of people ask me, why then are VFDs getting so popular? It's for this very reason. Let us say that today we have a greenhouse that their demand is 10 gallons per minute at 100 feet ahead. But they plan on being successful, so they're planning on growing. They're planning on adding additional, say, additional greenhouses and such. Now, granted, this is a very small number. 10 gallons per minute, 100 feet ahead is probably not what a greenhouse needs, but let's just pretend for this example it would. If we cut the impeller, and they grow, and now they double the size, and they need 20 gallons per minute, 100 feet ahead, you can't add material back to that impeller. But if they would have used a variable frequency drive, they could adjust the speed, which adjusts the head and adjusts the gallons per minute, and they could achieve that. And so that the pump with the full-sized impeller would grow with their needs. Once we cut the material, we're done. Now, I also point this out because, especially with centrifugals and larger units, we inadvertently trim the impellers all the time. It's called cavitation. Cavitation damage erodes not necessarily your flow, but attacks directly your ability to build pressure and head. So often we trim the impellers nowadays accidentally. To further explain this for you, to give you a better example, if you look at the eye of the impeller, okay, the eye of the impeller, say a cast iron impeller, okay, it's going to spin counterclockwise when you look at it directly, okay? Now, more importantly, it's going to spin 3450 RPM. Now, I told you this is a cast iron impeller, so it has an outer peripheral, and that outer radius is larger, of course, than the inner eye of the impeller. Thus, it creates velocity, okay? Now, which direction is it going to spin? Well, it's a solid object. Of course, it's going to spin the same direction as the eye of the impeller, counterclockwise, okay? But now, what RPM would it spin? Well, it's going to spin the same RPM as the eye of the impeller because it's a solid object. I'm not trying to, make you feel dumb or pick on you here or try to ask you trick questions. I want you to understand we're talking single speed here, okay? When you're talking a single speed, the outer peripheral will spin to 3450, the same as the inner peripheral. More importantly, though, is how much time does it take to travel around the radius? When you look at the eye of the impeller, and granted this line is out of proportion, but I want to demonstrate it's a shorter period of time to go around. So there's not so much velocity. As you go to the outer peripheral, because there's a greater radius, it takes a longer time for the water to travel the whole circumference. But here's the thing, remember it's a solid object, correct? I told you the cast iron impeller is solid. It spins 3450 RPM in the center. It spins 3450 RPM on the outer peripheral. Because there's a greater radius, you see that there's more velocity. The impeller imparts velocity onto the pump, onto the water. Okay? This velocity is what then becomes pressure and head down the road as we go through the pump. If you listen to my Pump 101 lecture, we've talked about this in greater detail. When we cut the impeller down, meaning either intentionally trimming it or through cavitation, punching little holes in it, we've changed that radius. But we've also changed not the rotation, not the RPM, but we've changed the velocity because there's less radius. Less radius equals less velocity, which equals less pressure, okay? So that's what we talked about. Now, let's get back to the curve because I promise you this was a curve discussion, okay? So, if we know that the curve is based upon gallons per minute and total dynamic head, what do I need to size a pump? Well, I need to know the total dynamic head in gallons per minute. Pretty simple, okay? So, when we talk about our water supply, let's first talk about a well. And in a well, we know that we're going to drill down to drinkable water. So we drill down, we put a screen material, and we put a pump in there. And we start to draw water, and we create a cone of depression. We create a drawdown. And this we want to know because that will affect how the pump will work. Now, I know earlier we were talking centrifugal pumps and how a pump curve is built. And now we're switched over to submersibles. But like I told you, submersibles, the pump curves are created fairly similar. So, but more importantly, with a submersible, we need to worry about this cone of depression. So when I start to pump my water, okay, it's going to draw a demand, which will then drop the water table because water can only replenish the well so quickly through the strata through which it's traveling, okay? So we have an equilibrium point. Let's say we find a happy equilibrium of 20 gallons per minute with maybe, say, 5 feet of drawdown. That drawdown is also known as the working level. It's also known as the pumping level, okay? So depending upon your demand, we now know, say for example, this well can give us 20 gallons per minute. The next question is, okay, assuming the well can support what we need, what does the home need? And we're going to be talking residential homes here. Larger projects are often very specific, and I'll explain that. Now, one of the things I want to mention is that when you talk about residential homes, there is no bulletproof formula to do so. A lot of times it's going to be dictated by the capacity of the well. If the well can only give you 7 gallons per minute, you will not put a bigger pump in than 7 gallons per minute, probably. You'll probably run 5 gallons per minute. And the homeowner will have to learn to budget their water flow. If the well only produces a half a gallon per minute, and a lot of people say, well, why would you even drill a well that produces a half a gallon per minute? A good example is out on the East Coast. They'll drill wells 700, 800, 900 feet, 6 to 8 inch casings, producing only half a gallon per minute, but the water table rises to say 50 feet, maybe 100 feet to the surface. That means from 100 or 50 feet, wherever that water surface that rises down to the bottom of the well in a 6-inch casing is water storage. And understand that for every foot of water in a 6-inch casing, that's at 1.5 gallons of storage. So they will pump that well clear down almost to the bottom using the well casing as a supply. But we're assuming here that we're not worried about it. The well has been drilled. It now can handle our capability. Now we have to know what the home needs. And like I said, there's no silver bullet. One of the ways to do so is by what we call is the fixture count method. Meaning that you look at a home inside and out, and every fixture, you don't care what it is, you give it a point value of 1. So we walked into a home, and as we walk in, we see they have a kitchen. So it has a sink and a dishwasher. So the sink and the dishwasher each get 1 point each. So we then move in, and there's one bathroom, a full bathroom with a lavatory, a tub, and a toilet. And each of those, we get 1 point each. We go into the powder room where there's a lav and a toilet again. So again, 1 point each. All right. Now we go down in the basement and we discover they have an automatic washing machine, which counts as 1 point. A laundry tub that sits right next to the dishwasher. We're still going to give it 1 point. Okay. Then we walk outside, and let's pretend this is down in Florida right near the beach, because you know what? If I'm going to dream and make believe, I'm going to dream I'm in a nice warm location. So this beach house has an outdoor shower where you can wash off before you get in the house so you don't bring in sand. So that shower gets 1 point. It also has 2 outdoor faucets for various reasons. So they each get 1 point. So outdoor faucets, there's 2. We give them 2 points. We then look at all our points and total them up, and it came to a total of 12 points. We take the point value, multiply it by 1 gallon per minute per point, and we would come up with 12 gallons per minute. Okay? Now, that's one way to do it. Now, here's the simple question. If I told you that was a retired couple living in Florida who don't really have many visitors, would 12 gallons per minute be sufficient? Be more than sufficient. Now here's the opposite side of the coin. This house is owned by a family with 5 young children. So there's 7 in the family. Would 12 gallons per minute possibly be enough for all they want to do at this vacation home? Might not. So again, that's why I tell you, it's kind of like horseshoes and hand grenades. We'll get you close, but I won't promise this is a proper answer. You have to know your customer and your customer's needs. So in this example, if the customer is a young family of 5, I might put in a 20 gallon per minute pump. So again, there's your discretion. Now, I've also heard other methods. Some people say that, well, for every bathroom, I give it 5 gallons per minute. So if there's 3 bathrooms in the home, I'll give it 15 gallons per minute. Okay. Some people do it by occupancy. How many people are going to live in the home? The big factor you can never ignore is your code. Your state, your federal, your state, and your local code. Always adhere to that code first. Okay. So if your local code dictates you size a well pump by occupancy or by bathroom or whatever, you have to obey that. Okay. So we kind of get a method, and you kind of get a feeling. It's hard to tell exactly how many gallons per minute each home will require. And I'll be blunt, it is. And that's where never feel you can't call customer service for any company. We're more than happy to help you. Now, here's the opposite side. If you look at that chart here on the right, this is a fixture flow chart. Often when you get engineers, a specified engineer or a project manager involved who look at worst case scenarios, they look at flow. A good example of this is that we had a dentist that was in a rural area, and he bought a very lovely Victorian home which he was going to add on his office to. And the minute he added his dental office to the residential home, guess what? It's commercial property. And guess who gets involved? An engineer. So this engineer looks at everything, and he doesn't look at the fixture count method. He looks at how much every fixture could possibly flow. See, he has to cover his interests, CYI. So that engineer wants to make sure he gives a number that's pretty bulletproof. And believe it or not, in a Victorian home with 2.5 baths originally, with the addition of the dental office, he had 2 stations that he was going to have for the cleaning and for the assistants, to take care of the basic stuff. And he had 2 offices that were for the larger dental practice, that he might have to do work in, for example, teeth extraction, whatever. But he had basically 4 rooms plus I guess you would call it a unisex bathroom, just a bathroom, both men and women. So now the home basically had 4 dental offices or chairs. It had a bathroom in the office and then 2.5 in the home. Now, believe it or not, the engineer came back that facility would require 78 gallons per minute. He basically looked at every fitting and every fixture count, but he didn't look at the fixture count. He looked at the flow potential of each one, and he came up with a ridiculously large number. Now, in this case, the dealer and both the installer came back to us at the factory looking for help, saying, hey, this is ridiculous. Can we not show them how they need less gallon per minute? And I'll tell you, the simple answer is you have to adhere to local code. If that specifying engineer tells you need that many gallons per minute, we unfortunately have to do it. So believe it or not, basically a dental office / residential home, we had to size them a 78 gallon per minute pump. So that's why, again, I tell you, there's no magical bullet. There's no one true answer. There's no guaranteed proof when you're sizing a pump for a residential application or even some commercial applications. Okay. So now we have our gallons per minute. We know the well can provide it. The other thing my chart's based upon is that vertical axis, which is your total dynamic head. Now, most pump companies express that in feet. And what is in total dynamic head? And when I say total dynamic head, I mean everything. Top to bottom, let's go through this. Friction loss. And notice my friction loss, I start because you have to know how far down the pump is set, because you want to calculate all of that friction loss. Make sure we get it all captured properly. Okay? And one surface pressure, we convert that into feet of head because my pump charts are in feet of head. Okay? You want to look at elevation. Are there any elevation? Is that well 1,000 feet from the home? And not only is it 1,000 feet, but it's also downsloped about 200 feet. Now we have to pump it not only that distance, but up to 200 feet. So elevation has to be taken into consideration. Don't tell me you can't find the elevation anymore. Let's be blunt. Most people have a smartphone, and there's an app for that now. Okay, you can find elevation by just walking around the property with your phone, and you get a very, not as accurate as maybe an engineer, but a very accurate number to calculate with. We also want to know where the standing water level is, and also where the drawdown level is. Remember that pump well condition we talked about earlier. The well could support 20 gallons per minute at 5 feet of drawdown. Okay, so more importantly, like I say, where's the standing water level, but how far down do you expect that water to drop? How many feet is that going to drop? And let me tell you, a lot of guys will ask me, well, okay, I got this well report, and it says the well is producing at 54 gallons per minute. It produces about 15 feet of drawdown. But Dan, for the home, I only need 12 gallons per minute. What should I calculate my drawdown to be? Would I take it as a portion? And my answer is no. Always take it for the worst case scenario. If at 54 gallons per minute the drawdown was 15 feet, I would say even at 12 gallons per minute, I would be anticipating 15 feet of drawdown. Some guys will argue with me, but I always say you got to CYI, cover your interests. Okay? Make sure you have all your bases covered. Now remember, total means total. And I don't mean to harp on this, but when I do any of my lectures, I try to teach you the vocabulary. And one of the things is when you come to a customer service agent and you say, I have the total dynamic head, that means we are assuming, and you remember the old Odd Couple show, what happens when you assume. So we shouldn't always assume, but we do assume that when you say total dynamic head, it means that you've taken into account all your friction losses, you've taken your service pressure and converted it into feet of head, and that your pumping level, which includes the elevation of the situation, the static water level, and the drawdown, have all been accounted for. Now, in that being said, we want you to understand how to do that conversion. Okay? Remember, and if you've taken any of my other courses, we've discussed, especially in the pump basics, 1 psi is equal to 2.31 feet of head. Okay? That means if I have psi, say 40 psi multiplied by 2.31, I will get my feet of head of 93 feet rounded up. Right? Or if I take 93 feet divided by 2.31, it would tell me roughly it's 40 psi. This is important to remember, not just for the conversion of the pressure into feet of head, but if you're doing landscaping projects, landscapers, Hunter, Rainbird, all those charts, if you read closely, they report not in feet of head of friction loss, but in psi. If you do not make that conversion and you look at a pump chart that's based upon feet of head, understand you're going to be off by a factor of 2.31 and most likely will undersize your pump. So, not to beat a dead horse, but I want to again reiterate, total dynamic head is friction loss in feet of head all the way down to the pump set. It is your service pressure in feet of head, your elevation, your standing water level is taken into consideration. More importantly, that drawdown. How far is my water going to drop during pumping? All right? So that is total dynamic head. Okay, it took us a while to get here, but I wanted to make sure we made this journey complete. A pump chart is based upon gallons per minute and feet of head. That's how we test it. That's how you size it. So looking at this chart, one of the things I often get questioned is when I look at this chart, the dead center point is the best efficiency point. That's just the golden rule. And I've heard that quite a bit out on the road this past year. And the answer is no. In this case, this pump is a 10 gallon per minute pump. In this case, 10 gallons per minute happens to be dead center. But don't assume that. Never assume that. Because, for example, a 70 gallon per minute pump might have a maximum range of 0 to 100 gallons per minute. Guess what? 70 is going to be skewed to the right. Okay? So don't assume that. Always, if you're looking at, say, a 70 gallon per minute pump, assume that at the 70 gallon per minute pumping mark is your best efficiency point. Okay? If they don't have the efficiency point properly marked on the chart. Now also you see on this curve, you'll see dashed lines. On the left side, we want you to stay away from that because that's your minimum constant sustainable flow. If you're using a variable frequency drive, you definitely don't want to be over there because you're going to have uplift issues and other cavitation issues. As you go to the far right of the curve, if you've been to any of my other lectures, you'll know that I've explained this. When you go to the right of the curve, you start to over amp the motor. You put in a heavier workload to the motor and the amps will increase. So you definitely want to stay out of the dashed lines for that reason. You don't want to exercise the motor too heavily, especially if it's in an irrigation project and it will be running there for a prolonged period of time. Now, looking at the curve again, we see that the gallons per minute is on the horizontal. The vertical shows head of feet on the left side. Now, if you're also looking at the right side of this curve, we show feet of head in meters. And on the very top, we have the horizontal again showing capacity of flow, but this time in liters. So this is a kind of an international curve, if you would. Now, I want 10 gallons per minute, and I want it, say, at 500 feet of head. And if we look at that curve, 2 horsepower pump looks pretty good. Okay, you see how we can do what's on the curve? You might think it might be a little less, might be a little more. We're not too precise about that. Now, some companies show you pump curves, some companies will show you pump charts, or some of them, like us, will give you both. I want you to think a minute. When you look at pumping depth in feet, if I told you I gave you a total dynamic head at 500 feet, what's the PSI service pressure would I look at? Okay, so we have our pumping depth there. We have our horsepower. To answer that question, I would look at 0 PSI. Why would I look at 0 PSI under the 2 horsepower mark? Because we want to proof the 2 horsepower. That's the one that we looked at the chart. We thought the chart, that looked good. But why would I look at 0 PSI? And it's because, what's the definition of total dynamic head? Friction loss, service pressure, elevation, and drawdown. Right? Service pressure is included. So, I would then look at 0 PSI because I've already calculated it, but I would look at depth of water as being 500 feet. And if you look at 500 feet, 0 PSI, 10.2 gallons per minute. So I'm feeling pretty good about that number, all right? Now, what if the customer says, I have 350 feet depth of water and 60 PSI? If you notice, he'd be basically getting the same number of 10.3. Okay, because 60 times 2.31 is roughly 143. Okay, at 143 to 350, that puts you very close to 500 feet. So you can do it either way, don't get me wrong. But understand, in that 300 feet depth to water, Do we know, did he take into consideration any friction losses and such? We're not sure. Okay, we're not sure. But that is one way you can do it. Now, I'll be honest, I'm not overly concerned. If you want to do it just depth to water and your PSI requirement, if you have less than 500 feet of 1.25" or 1-inch pipe and total run, your friction loss isn't going to be that terrible. So you're pretty safe to just look at the chart directly. But I myself, especially with smartphones and other things, it's very easy to calculate the friction loss now. I would rather you see it do it the total dynamic head way, which is you calculate everything out. Now, remember, total means total. And I'm, again, not to belabor this point, but as a customer service agent, when I was working the phones, let's face it, if anything goes wrong, who's going to get the blame? Well, it's going to blame that guy at the factory. We often got blamed for a lot of things. And so we started pushing back. And when we heard total dynamic head and, I need 60 psi, understand, if we're looking again at 10 gallons per minute, we draw that line at 10 gallons per minute. You said, I need 10 gallons per minute at 500 feet ahead, and I need 60 psi. Well, that 500 feet of head, could that include 60 psi in the calculation? Absolutely. Remember that example I just talked about with the chart, going 350 feet depth to water and 60 psi? It was the same as doing basically 500 feet of head at 0 psi. In 500 feet of head, 143 feet can easily fit in there for the pressure calculation. But if I make the assumption that, you need an additional 143 feet, now look at that. I'm looking at easily a 3 horsepower pump. I'm well over the 2 horsepower mark. I can't use my 2 horsepower, so I'm going to size you with 3 horsepower. And I'm going to oversize that pump if we misunderstood. Customer service people, and I'm not talking about at Pentair, I'm talking about any company, we're not trying to be difficult to work with, but we ask questions because things like this always happen to us. Okay, remember, total dynamic head is friction loss, elevation, service pressure, converted into feet of head, and your drawdown factors. Okay, now let's look at an example here. We're going to look at a residential home. And I've drawn out the total dynamic head here for you. So we have a customer that has a well that is 6 inches in diameter. Now we have a standing water level of 42 feet. We have a drawdown of 10 feet. I asked the customer, well, what's the well production? And he said, well, it's well over 20 gallons per minute. Don't worry about it. Okay. Am I going to worry about putting the drawdown into my calculation? Absolutely. Am I going to worry about running the well dry? No, because he assured me that it could provide the gallons per minute required for the system. Okay. So our drawdown plus our standing water is 42 plus 10, which is 52 feet. Okay. Well depth, the well depth is 82 feet. Now, whenever you come to one of my seminars or you go to my class or you talk to here on the webinar, we always say that for calculating and everyone getting the same answer, we always set the pump 15 feet off the bottom of the well. So this is not an industry standard. This is just so we all get the same answers. So when I set my pump, knowing the well depth is 82 feet, I'm going to set that pump at 67 feet. Why do I care about how much pipe is going down the well? It's because we're going to calculate the friction loss. Okay. Horizontal pipe run. Apparently this is an existing well and he already has 1-inch pipe PVC already installed. In fact, he has 70 feet of it going out to the wellhead. So that begs the question, is there any elevation? And the answer is no. The elevation, it's flat. Okay. System pressure desired, 30-50. Now, I'm going to do this the traditional way, in which we take 30-50, we average it, and it's 40 psi. Not to get into too much detail, but I'm now discussing and teaching often maybe look at 50, especially if they're going to use a variable frequency drive. I would look right at 50 if they want the higher mark, or 60 if they want to set it there. But traditionally, we always looked at 30, 50, averaged it to 40, so that's how we're going to do it today. Fixture count, he went through the home and he counted 10 fixtures. Remember our method, 10 fixture points times 1 gallon per minute per point will give me 10 gallons per minute required for the home. Irrigation use, he has none. Power supply is 230 volt single phase, which that's what I expect from a home, so that's great. Now, not to get into too much detail, but we're looking at a friction loss chart here. So quickly we're going to look at 10 gallons per minute, and we're going to look at 1-inch pipe. And at 10 gallons per minute at 1-inch pipe, we see the velocity is 3.7 feet, so we're not worried about water hammer. We have good velocity. We also have 6.31 feet of friction loss in that plastic pipe for every 100 feet of pipe. Okay. Now, I mentioned the velocity because I always like to keep it, especially in the discharge, you have to make sure you keep it under 7 feet per second. And that's why we're going to stick with 1 inch, because we're only running 3.7 feet per second. So we chose 1-inch pipe. Now the system designed gallon per minute. We determined it was 10 gallons per minute. We knew that the pipe we were going to keep running with is 1 inch. And we know that the friction loss per 100 feet of pipe is 6.31. The total pipe is 67 feet. Where did I get 67 feet? That's the pipe drop pipe. Remember the pump setting, 15 feet off the bottom? The well is 82 feet. 15 from 82 gives you 67 feet. So we have 67 feet, plus we have the 70 feet of horizontal pipe. So 70 plus 67 is 137. Okay? Now, I take that 137 and I'm going to divide it by 100, because that's what my chart was based upon, is 100-foot lengths. And that gives me 1.37 feet, or 1.37 units. Times the 6.31 tells me my total friction loss and 137 feet of pipe is 8.64. This is where I cover my interest. Okay? I'm going to round that up to 9 feet. Because if you notice, I didn't calculate for any fittings. Okay? We have at least one fitting for the pitless adapter, possibly one more to go into the tank. I didn't account for those. I just rounded up the number. Okay? Total dynamic head then is pumping level. The pumping level is 52 feet. Where did Dan get the 52 feet? Remember, the well depth is 42 feet. The well test showed a drawdown of 10 feet. Now, granted, it was much more than 10 gallons per minute, but I want to cover my bases. So the 42 plus the 10 feet of drawdown gave me 52 feet for pumping level. I have no elevation to add in there, so that's why it's just 52. Service pressure in feet of head, I took 40 times 2.31 and rounded that up to an even 93 feet of head. I add my friction loss, which we just calculated above at 9 feet. I total them up, and my grand total comes up to 154. All right. So I look at that 10 gallon per minute curve, and here I blew it up for us so we can see it better. And I draw my line at 154 and see where it crosses 10 gallons per minute. And that half horsepower pump looks pretty good. Now, looking at the same pump, remember, and what's the problem with 40 psi? Let's look at the pump chart this time. Okay. So we have 10 gallons per minute. Okay, we're going to look at our pumping depth. We have our horsepower. We have our different horsepowers there, half, 3/4, and 1 horse. Okay, we have our PSI. We're going to look at 150 feet of head, because I don't have 154 feet. And now remember, I just told you my total dynamic head is 154. Oh, and I need 40 PSI. So does that mean I look at 150, go to 40 PSI, And now that half horse is only doing 2 gallons per minute. It's not satisfying the need. So I go down. 3/4, I'm getting 8.9. Well, I'm getting closer. But a 1 horse. I'll give you a 1 horse because you told me 154 feet ahead and oh, I need 40 psi. I would have doubled the horsepower requirement for that pump that we just sized. Okay? This is just to emphasize, not that I'm trying to be nitpicky, but this is how people get tripped up. We got to make sure we understand the language and we understand what we mean when we say these words. Okay? When you told me total dynamic head at 154 feet and 40 psi, you just said, oh, wait a minute, I don't have total dynamic head. So that's where we have to be careful. That's where sometimes customer service agents will pick apart the numbers. What we're really looking at is 150 feet ahead at 0 psi, because remember, the 154 includes the 93 feet for the 40 psi. And at 0 psi, at 150 feet ahead, we're getting 10.8 gallons per minute. Okay? And that number confirms what we saw in the chart when we sized it properly. Again, I'm not trying to pick on anybody. I just want to make sure we're speaking the same language. Now, if you go and look at, say, the drop down of the well, we know that the water table is at 42 feet. It's going to drop the additional 10 feet for a total of 52. I don't have depth of water 52, but I do have 60. Now, let's look at 40 psi. And at 40 psi, look at that, 10.8 gallons per minute. So we confirmed it 2 different ways. Okay? Remember, total means total. When you say the word total dynamic head, we assume friction losses all the way down from the horizontal to the drop pipe going down to the pump. Service pressure converted into feet of head, and the pumping level, which is your elevation, your static water table, and more importantly, the drawdown expected. Okay, so now let's look at another example here. We have a submersible well pump. Again, we have a 6-inch well, which is great. It means we can put in a 4-inch very handily in there. More importantly, the stand-in water table is at 150 feet. Your drawdown is at 75. And again, the customer says the drawdown was tested well above the demand. I asked how well above. He said, well, we don't have an exact number, but we know it's more than we need. So knowing that, I'm going to have my worst case scenario in mind, which means my working level would be the 150 plus the 75 for a total of 225. Okay? So the well depth is 300 feet. That means we're going to set the pump 15 feet off the bottom so we all get the same answers. So we set the pump at 285. And we needed to know that to calculate the friction loss for the drop pipe. The horizontal pipe run. Well, once again, someone installed, so we must be just replacing a system. We have 1.5 inches already installed for 75 feet. Elevation. Well, we got elevation this time, folks, 25 feet. So we do have to calculate that into our numbers. System pressure desired, again, 30-50, so we're going to average it to 40. Fixture count on this one was 20 gallons, or fixture count on this one is 20. So remember, 20 fixture count units times 1 gallon per minute would give us 20 gallons per minute estimated for the system. Irrigation use, none. We're keeping this nice and easy. Power available, 230 volt single phase, which again, we would expect at a residential home. Looking at the friction loss charts right away. We know we need 20 gallons per minute. We know we have 1.5 inch pipe already installed. So let's take a look at that 1.5 inch section. And at 20 gallons per minute, 1.5 inch pipe, we know the velocity is 3.2 feet, which again is well below the 7 feet per second, so we're happy with that. We also know that at 20 gallons per minute, for every 100 feet of pipe, we have 2.83 feet of friction loss. So We're selecting our pipe 20 gallons per minute because 20 gallons, I'm sorry, because 20 fixture count units times 1 gallon per minute is 20. We're going to use 1.5-inch pipe to keep it the same to make our calculations easier. The friction loss for the pipe per 100 feet was 2.83. The pipe totals. We have the horizontal pipe run plus the pump setting. The pump setting was 285. Remember, 300-foot well, 15 feet out the bottom. We'd have 285 feet of pipe going down the well. We have also the horizontal pipe run we also have the horizontal pipe run of 175. Adding those together, we have a total pipe run of 360. I'm going to take that 360, I'm going to divide it by 100 because that's what my chart is based upon, 100-foot lengths. I get 3.6, multiply it by the friction loss per 100 of 2.83, and I get a grand total of 10.19. What am I going to do to that number? I'm going to round it up to cover my interest to make sure I account for fittings and such. So I round it up to 11. Total dynamic head then is your pumping level plus elevation. Remember, there's elevation this time. For a grand total of 250. Okay. We got to account for our worst case scenario for drawdown plus the elevation. So we want to make sure we get all the numbers covered. So we're going to plan on 250 feet. We also have to add in, or for our total dynamic head, our service pressure. 40 times 2.31 is 93 rounded up. We just calculated our friction loss. Right above there, it's 11 feet. If we total all that up, we get a grand total of 364 feet. So at 20 gallons per minute, 364 feet, we'd be looking most likely at a 3 horsepower. Now I also want you to understand, at 20 gallons per minute, it's potentially possible that that 3 horsepower pump would actually be running about, say, 440, 445 feet of head. So an additional potentially 100 feet of head. Would that possibly damage something in the home? Well, yes. But remember, in a residential application, we're pumping from the well directly into a pressure tank. That's why the pressure tank is critical. That pressure tank can absorb the extra pressure and flow to balance it out in the home so the home does not see that extra flow or that extra PSI. Okay? So maintaining the tank is critical. If we look at the chart, okay, remember we have total dynamic head. So we look at 350 because I don't have 354 to look at here. And again, 0 PSI. And at 0 PSI, at 350 feet, 23.5 gallons per minute. So we're a little bit over the mark. But again, at that point, we have the tank for a buffer. Okay. If we looked at the 250 feet depth to water and then our 40 PSI, we get 23.8 gallons per minute. Okay, very close to either calculation. The reason you see a difference there is because, again, we're not calculating the numbers properly in that 250 we're rounding, 350 we rounded down from 354. Okay, so we're not calculating for all of our numbers by doing this. But if you see the method of depth to water versus PSI, it's pretty close to if we calculated the whole thing. That kind of brings me back to the point that if you have less than 500 feet of pipe, often you can just look at depth to water and your pressure and get you a pretty good solid answer. I want to thank you for your time. I hope that wasn't too quick. Understand you can always review these. We have other modules to look at. We have other webinars always coming up. Also understand your input counts. A lot of these modules we do are because of customer request. So if you have any ideas, shoot them to training.institute@pentair.com. Otherwise, this is Dan Featherstone. Thank you very much, and look forward to speaking to you in the future.